Good afternoon, everyone. I'd like to welcome all of you to technical section 5 of SVR. In this session, we'll have 5 presentations, and after each video is played, we will have time for answering some questions. So about 2 to 3 minutes question and answer time. So the first paper will be presented by Salvador Agati, followed by Rudieri Bauer, and then a paper by Gabriel Viegas, followed by Jean-Michel Fazzari, and finally Fabiana Perez. So the first presenter can start it, Salvador Agati.
Hello, my name is Salvador Sergi Agati, and I am a PhD candidate from the Electrical Engineering Department of Santa Catarina State University in Brazil. We started our research trying to answer the following question. What are the guidelines used to create AR-based manual assembly lines systems? Our agenda is as following. First, we contextualize the problem, considering AR as a possible solution. We did a systematic literature mapping, trying to find guidelines to design new AR-based systems for manual assembly lines. We present the results found, the conclusions, and limitations of our research. Nowadays, consumers tend to customize the products they buy. This behavior leads to small assembly lines to customize some parts of the product. But for small assembly lines, the cost of its complete automation is prohibitive. With humans being part of assembly lines and with machines become more reliable, human errors became a critical factor to product quality. About 70 to 90% of the defects found in manual assembly lines are related to human errors. Considering that AR may be a possible solution to reduce human errors and increase products quality, we considered gathering general guidelines to design AR systems for industry. The strategy was to review previous systematic literature mappings that were focused on AR for assembly line in industry. You may observe that we did not include the word industry in the search phrase because of our intention to gather the highest number of review papers. In this table, we can see the academic search engines used, the initial number of papers, and after exclusion and inclusion criteria, the 14 review papers resulted. After the complete reading of the 14 papers, we were able to find explicit design guidelines in 11 of them. We categorized the guidelines found, resulting in 4 groups: usability, cognitive, ergonomics, and corporate context. Related to usability guidelines, user interface must be simple to not deviate the user's attention from the task, as well as the feedback provided to him. Multimodal interfaces allow multiple sensorial inputs to facilitate the human interface. As the user learns the task, feedback can be adaptive, respecting his pace and cognitive workload. Related to cognitive guidelines, the implementation of an AR system must consider the effects of transitioning between the old and the new processes. The transition to new practices must be as soft as possible. The cognitive workload of the user can be diminished, giving him control of the speed of your work. Progress bar or gamification strategies, for example, can be used to maintain user motivation in the long term. Related to ergonomics guidelines, the design of an AR-based manual assembly system must be considered the effects on a user when wearing the AR device in a daily basis, improving the device's characteristics that affect user ergonomics such as battery time, weight, and field of view should be a best practice. Users' feedback must be accounted to improve the hardware used in cases it's not possible to equip the environment. Related to corporate context guidelines, to implement an AR system, the industry managers must be convinced of the benefits such a system will produce. A proof of concept must show better error rates, faster assembly parts, better quality, and fewer products reworking. As the user side, less fatigue, fewer workloads, and better productivity must be achieved. Personal data must be secure and privacy policies must be defined. All these key performance indicators must be provided in the system so that industry be convinced of its usage. We found that our research has some limitations. For example, we did not consider the implicit guidelines that can be deducted from the review papers reading, as we considered only review papers, mainly because some of them were very recent. We obtained a small number of papers. Maybe there are new guidelines in the primary papers the review papers were based on. Another consideration is that we categorized the guidelines found after reading all the papers based on what we found. So, the categories probably do not cover all the possible existing categories. If new guidelines are found, possibly they may fit into new categories. The last consideration is that we collected general guidelines so that they would be useful in the majority of new designs. So, it is reasonable to think that there are another group of categories that are related to each project, and this group may be found during the project scope definition. Thank you very much for your attention.
Okay, let's see if we have any questions here in Wova. It looks like we don't have any questions, but I'd like to ask you, since I see that these two paper this paper and the next one are from the same group, I believe. So is this motivation, the motivation for this work is some uh, project with industry support or what? Can you tell me a little bit about this?
Yes, are you hear me?
Yes.
Yes. Yes, we based the project seeing in a real context in the problems in the industry have. So we decided to consider these problems to start our project.
Okay, there is another question coming here that is, are there any methodologies to build AR-based manual assembly systems?
Uh, as far as we studied, there are methodologies, but there are not a standard. In the papers, all the authors use uh, a kind of a path for doing the design, but there is uh, a standard methodology until now.
Okay. Doesn't seem to have any more questions, so I think we could start the next one. Then.
Hello everyone, my name is Guilherme Bauer, and from now on I will be presenting the work entitled Manual Printed Circuit Boards Assembly using Augmented Reality towards Total Quality. For a brief introduction for the work, we are bringing on the concept of Assembly 4.0 that unites another concepts that already existed in the literature, like the Industry 4.0 when we talk about the IT integration in the production process. When in this work we are bringing on production system based on augmented reality technologies for improve the manual production assembly lines, improve the quality using the concepts in premise of the total quality management to develop a system for that uses augmented reality technology in the context of manual production assembly of printed circuit boards. To make this work, make this study, we firstly look for another related works in the literature and find it's 5 different works that bring different ways to solve this problem. We find works about the use of intelligent augmented reality for motherboard assembly using handheld devices like smartphones or tablets. The use of augmented reality-based training for PCB assemblies using hand-mounted displays like HoloLens or Google Glass. The augmented reality and sensing device for manual assembly workstation using the multimodal devices, and for the augmented reality using the head-mounted displays. Long-term analysis of on-situ instruction at the assembly workplace using fixed webcams in the workbench and projections to show the augmented reality information, and works about the impact of monitor-based augmented reality that uses a combination of fixed webcam and traditional monitors. So we have 4 different hardware setups that we identified in these related works. From all the benefits that the works bring, the 3 main identified by us was the last assembly errors in the production assembly line, the lower mental stress rates from the workers that produce the printed circuit boards, and the fastest assembly times of the assembly lines when using the augmented reality system. In that way, we started working in our case of study, working with a real fabric in a real industry that produces printed circuit boards to investigate the limitation peculiarities and information included in the assembly line in the printed circuit boards production environment to bring on things that could be important from the system, like on the assembly line, the worker receives the printed circuit board in a certain assembly stage, and after that, they must insert appropriate parts and send to the printed circuit boards. So now to the next step, when another worker in another bench will make the assembly of the parts that they are designed to be. The assembly stage are divided into different workbenches with only one worker per bench, and all the parts required for the assembly stage are arranged in front of the bench and present very different size, different shapes, different colors, and must be inserted in the certain order to prevent errors in the circuit board. Also, for ergonomic reasons, it's desirable that operators be free of wearables. So the both hands need to be free to manipulate and put the parts in the printed circuit boards. And also for this, some monitors are presented in the workbench that display electronic manuals that already are in the assembly lines. And from this, uh, because of this, for the fork hardware configurations identified by the related works, we choose it to use the fixed webcam and traditional monitor approach because of the lower cost of implementing the system in a assembly line that already has monitors on the assembly line, and also because of the ergonomics of not putting any wearables on the worker. So from the development tools chosen by the project, we tested for different software development kits, the R2 kit, the Wiki tool, and the DZR and the Buforia. And then ended up choosing the Buforia because of the most precise presentation of augmented reality objects in the printed circuit board itself, using the printed circuit board image as a fiducial marker. So the Buforia was the one who presented the best results in the stability of the augmented reality objects. And from that on, we designed a system architecture that propose a system that should provide a lot of information for the worker in the assembly line, like what parts are supposed to be assembled in this step of the PCB, when those parts should be assembled, when I should use a tool to assemble that, how many of those parts will be assembled on the circuit board, where they are to be assembled, and from where they are on the workbench, what way, some orientation that should be used in that part specifically, and how much, what are the conditions to these parts. There are any parameters to be concerned about. So we designed the system with 4 different modules: an entry model with a fixed webcam, a process model with augmented reality user interface, pattern recognition, product management database, and the presentation of the augmented reality information by the traditional monitor. And with this, the conclusions of the work shows that in the related works, there are no methodologies that are standard for this type of system. There are no patterns to be defined yet. And also the system presents clear benefits on the studies that we already have published on the literature. And so for future works, we want to go deeper in the daily life of the assembly worker to implement and test the system. And that's it. Thank you very much. Hello, everyone.
Okay. There is one question here that says, is there any reason for not including in the research AR core and AR kit analysis?
So the AR kit, I remember, is from Apple, right? Then we firstly don't use them in the research because we don't have access to any device of Apple. We don't have a way to test it, so see how it works on the assembly lines, and the SDK tests were made after the definition of what hardware will be using. So we filter the software development kits based on the fixed monitor, the fixed webcam, and traditional monitor approach. So then we choose to work with this part.
Any other questions? Well, I see that you haven't finished the implementation phase yet, right?
Right. We have worked with enterprise to see how the system will work in the assembly line itself. But because of the pandemics, we cannot implement the system in the assembly line, and we just made a prototype of that will that we not tested yet in the assembly line.
Okay, and the idea is you think the system will reduce or minimize errors or reduce training time, or both?
Based on the works that already are in the literature, the results show that our systems tend to minimize error rates, assembly time, and lower mental stress. But we will need to work with different types of workers to see if there are any difference, some difference in implement the system for someone that is already trained on that, someone that already know how to do the tasks, and someone that is beginning in the fabric, someone that don't know how to assemble a PCB, to see how the adaptation from the system will work, and the system will be better to training the new workers, or to be used as in the assembly line on a daily basis.
Okay, thank you. I think we don't have any more questions, so we can start the third presenter.
Thank you.
Hi, my name is Gabriel Freitas, and I will present our research article called A Systematic Review of Rapid Prototyping Tools for Augmented Reality. Prototypes are used to ensure the quality of software projects by testing the idea before any type of development. Low fidelity is a type of prototypes that can provide a cheap and simple method to gather information about a product right in the early stages of design. However, the creation of low-fidelity prototypes for augmented reality applications can be more challenging compared to the other technologies due to the unique characteristics of augmented reality applications by combining the real world and the virtual world. Here we have some features that AR prototypes needs to concern in order to create a useful prototype compared to traditional technologies like web or mobile applications. First, the 3D environment. AR prototypes needs to concern about the dynamic state of the 3D environment. Second, the tracking sensors. AR prototypes needs to concern also about the tracking of these digital objects. And third, AR prototypes also needs to concern about the user movement based on the digital element's position. This is an example of a low-fidelity AR prototype. Here, we can see an improvised label made with paper and a pencil, simulating an AR app idea. So the main problem is there is a lack of tools to quickly iterate and create new ideas utilizing low-fidelity prototypes for AR, methods for AR projects. On the other hand, 2D screen-based interfaces offers many tools to create prototypes. Here we have three examples like Sketch, Figma, and Photoshop. So the purpose of this study is to systematically review the state of the art in the AR rapid prototyping area, finding the tools, trends, and opportunities regarding this topic. With this in mind, we provide our methodology plan. We're starting with the search strategy. First, we define our research questions, our search databases, and our inclusion and exclusion criteria. After that, we aim on our search selection process, and finally, with our primary search results, we apply a snowballing method to ensure that the majority of sources are included. For our first research question, that is, which artifacts, tools, and frameworks and software can be used to facilitate the creation of low-fidelity prototypes for augmented reality. Here, we show all the artifacts founded distributed by level of fidelity and skill required. The y-axis values are based on the skill set of an end user and non-technical person. The x values are based on the artifact level of interactivity and concept presentation. For example, Unity is a much more complex tool compared to a paper method for a non-technical person. So in the left bottom, we can see artifacts that do not use a digital tool to create prototypes like storyboard, paper, and Wizard of Oz. Also clay. Close to the center, we can see an inspection of daily applications that can be used also to create AR prototypes, like PowerPoint and Keynote. For our second research question, that is, what are the most used artifacts for a low fidelity prototype in AR? We found that paper was the most cited artifact when we talk about low fidelity prototypes. In this picture, we see a two-layer paper AR prototype. The cardboard layer represents the mobile device field of view, and the paper layer represents the real world. This method is called PAPAR. PAPAR shows that traditional methods like paper and storyboards can also be used to create low fidelity prototypes for AR. By representing the device field of view with another layer, we can simulate an AR app in a low fidelity way. So for our final research question, that is, what are the common challenges being faced when prototyping for AR in a low fidelity way? The first challenge that we found is the creation of the 3D objects that will compose the AR application. The validation of gestures and interactions in general can also be a challenge in a low fidelity way. The camera simulation is also a challenge, but the PAPAR method mentioned earlier can be an answer for that. The communication of concepts can also be hard, but can also be represented by a paper or a storyboard method, also mentioned earlier. And finally, we review a lack of studies about low fidelity prototyping for AR applications. This study uses great literature sources. So many of the artifacts and studies presented were not independently validated. So this is one of our limitations. Thank you.
Let me see if there is any question coming from Wova. Well, I guess this systematic review has some broader purpose. What do you intend to do with the results next?
So the idea is to study a method that can approach this ideation phase for applications like augmented reality. Today, we have a lack of studies about this topic. So the idea is to create a method that can help in this ideation phase for development teams.
Okay. See, I don't see any more questions. So thank you again, Gabriel, for the presentation. We can start the next video.
My name is Jean-Michel Fazzari. I will present you my work, PRISM, toward a model linking tangible interaction and domain-specific tasks in mixed reality environments. The project we are working on aims at reducing the cost of designing and manufacturing operator platforms, such as cockpit of an airplane or a cache dashboard, for example. This cost impacts not only the platform manufacture itself, but also the study and evaluation of the platform by ergonomists. This consists in the modeling of the system and the activities which lead to the manufacturing of the model at scale 1, on which experiments are carried out. The process allows errors to be identified and different alternatives that may lead to a model modification to be tested. The later errors are detected in the evaluation process, the higher the additional cost will be. The addition of an interface simulation step between modeling and mockup reduces the risk of error, but allows little simulation of the system. This is why we propose the use of virtual reality as a simulation environment. This allows not only rapid prototyping, but also a better immersion of the operator in the simulated environment. However, two problems arise. On the one hand, the design of these virtual environments requires specific developments, and on the other hand, the lack of naturalness of interactions. This is why, in order to increase the immersion of the operator in the virtual environment and to improve the naturalness of the interactions, we propose to add tangible interfaces to these virtual reality environments. Based on this observation, we make the hypothesis that a generic interaction model allowing the automatic link between interactions and domain actions will reduce the design cost by the ergonomist. From this hypothesis, we deduce three research questions. How to describe in a generic way the different types of MR and tangible interactions? How to describe the platform and the activities of the operator? How to establish the link between the operator interactions and the action in the activity? In order to answer the first research question, we have described a typology of interactors, including voice devices, tracked tangible objects, gestures, WIMP interfaces, and controllers. We have exhaustively defined the types of interactors of which a particular device is an instance. All these types of interactors are a specialization of the same interactor class. We thus estimate to have covered the vast majority of devices used in mixed reality. For example, an augmented reality headset could be described with gesture and voice. Then, in order to describe the platform and the activities of the operator, we choose the Mascaré metamodel, which allows to formalize the semantic content of the environment and to describe the human activity by activity diagrams. The operations represent all the agent domain capabilities, as here in our example, changing the radio frequency. An activity refers to a set of actions. And finally, an action can refer to one of the operations referenced by the agent. Finally, in order to make the link between the operator's interactions and the action in the activity, we integrate the notion of interaction. This notion is composed of an interactor that we specialize in a manipulation, one of the four types of interactions according to Bowman. An interaction also refers to an action. An action can be a realization of an operation as described here in the example activity. To date, the link between the interaction and the action is realized without additional code, but using an XML file. We are currently developing a GUI that allows the ergonomist to fill in this information in a more natural way, and then to modify in real time the modalities of the interaction, allowing the execution of the action. Thanks to this work, ergonomics can not only monitor the activity, but also create domain procedures in real time without development. We have designed a dedicated GUI that allows us to follow these steps in real time. During the simulation, the operator will perform interactions, which will be identified as they are performed according to the activity diagram. When the ergonomist wishes to create an activity, the identified interaction of the operator will automatically create an action in the activity diagram until the ergonomist stops the simulation. In perspective, to test our hypothesis, we are planning two complementary evaluations. One is a developer-oriented evaluation, which will allow us to assess the development load of a virtual environment with and without our model, and on the other, an ergonomist-oriented experimentation, which will let us evaluate the feasibility of describing a system and its activities in the virtual environment with app development.
Thanks, Michel. Let me see if we have any questions from Wova. There is one question saying, congratulations for the work. Is the tool open for use?
Project, and this NERD project is led by a private company. So I think it will not be in the it will not be open for use for now.
Okay, so is this company related to the airplane industry, or?
No, it's an institute of technological research.
Okay. So the applications they are envisioning are more in what areas specifically?
In fact, this implementation is just a use case. My work aims to be a generic models. We use this particular use case because we add all the interactor to describe all the activities.
Okay. Okay, any more questions? I don't see any more questions. So thank you again, Michel. Nice work. Let's go to the last video presentation now.
I'm going to present a paper with an analysis of XR research in Brazil from 21 years of SVR publications. This is a collaborative work between João Marcelo and me. We provide an analysis by reviewing the development made since the first WRV event until the last SVR. This analysis can help understand how the area was explored and provide a roadmap for future research. We reviewed the full papers from previous conference proceedings. There are 557 full papers. They providing an interesting snapshot of emerging research trends in XR. Our analysis was specifically guided by the following three questions. Which areas have been explored in XR? What are the developments and key problems in these areas? What are important future trends for XR research? We grouped past XR research into the 11 topics. They are based on the key topics used in the previous editions of the conference. The papers were broken down into two groups. The first group contains the 5 main research topics in publications, which is interesting because they are not all in the core technology areas needed to deliver an XR application. This means that most SVR publications are focused on using technologies to solve applied problems instead of developing new basic core technologies. Despite its internationalization efforts, SVR is mainly comprised of publications from Brazilian authors in its majority. From the analyzed publications, only 39 papers are from foreign authors. The geographical distribution of Brazilian authors is shown in the figure. In addition to analyzed paper topics, we also measure their relative impact by calculating the number of citations of the papers. The total number of citations was found on Google Scholar, and the evolution then per year illustrate a very curve composed by many peaks and valleys. Such behavior leads us to believe there is a two-year interstice between published works considered more relevant to the scientific community. We also grouped and analyzed papers according to their application areas. The figure shows how the published papers were distributed in the main application areas. Since the two first categories represent papers that have no specific target area or a target area different from those mentioned, the most important application areas focused by SVR papers were education and health. One important point when developing new technologies and solutions is how to evaluate them. Usually, user studies are applied to validate them. And for this reason, this was also analyzed on the papers. It's possible to perceive a growing tendency for both. The papers analyzed were compiled into an open catalog available on the internet. Gartner Hype Cycles of Emerging Technologies in 2017 shows VR in the slope of enlightenment phase, while AR is in the trough of disillusionment. It's important to nowadays observe that the Gartner Hype Cycle for 2019, there is no mention to these technologies. This means that they are mature, and many companies believe in their potential. While this is true, some hot topics deserve attention. The increased interest in user studies for validation solutions, real-time understand of video content captured by cameras, and how companies may benefit from this intelligent analytical resource. XR adoptions for immersive learn and collaborative virtual environments. The world is changed because of the new types of experience enabled by these technologies and the connections they can foster. In an era of social distancing resulting from the coronavirus pandemic, the need for collaboration in virtual environment is unprecedented. This research classified the 557 analyzed papers regarding the main conference topics and inferred their relevance according to their citation numbers. Currently, to bring XR research from laboratories to industry and widespread use is still challenging. Thirdly, more researchers are paying attention to these areas, and it is becoming easier than ever before to be involved in XR research. We would like to thank Francisco Simões and Kleber Correia for contributing to the data acquisition process of the papers. Also, we would like to give a special mention to Luciano Soares and his incredible hub for collecting SVR proceedings throughout the years.
Thank you, Fabiana. We have one question from Wovadi. It's asking if you consider both full and short paper from the conferences in this research?
Yeah, that's a very good question. Actually, we have considered only the full papers. Since we have analyzed 21 years of conference, we had to look at more than 500 papers. So if we have considered both full and short papers, I believe the paper would not be done to this conference. It was a hard work, actually.
Well, one thing that I found interesting, I mean, I think is maybe a suggestion is when we see the distribution of papers by region in Brazil, that's a useful information. Is good just to see how the things are evolving in each region. But one thing would be more interesting for me, at least, would be the possibilities of cooperation, and it's good to see the correlation between areas and regions to see who is working with who in each region, and then establish like the possible connections for corporations. This is, I think, could be extracted from your data.
Yeah, actually, this is a very good point. We have this data already. Since we have cataloged all the full papers, we have the information from the author's location. And one of the fields that we analyzed is the collaboration between different regions, different authors, different universities, university, industry, and stuff like that. But since we had a very limited space in the full paper section, we were not able to put every information that we got from the research. So that's why we created the open catalog, and all the information is publicly available.
Okay. Thanks again for the presentation, for the work, and I think this ends our technical section 5, and we thank all the audience for taking part in this discussions and presentation.